today we're talking about model of execution. Quick reminder, I always have on my phone the Discord lecture channel open. I'm watching that. I don't always respond to it in lecture. You know, I'm doing something else up here. It's a little hard to keep my eye on it. It was easier with Twitch chat when I was sitting there at home, but I'm finding it a little tougher. But we do have some wonderful TAs who are in there during lecture, and they're happy to answer your questions. And then if there's something that needs my attention, I'm sure they'll flag me down and let me know. And as always, feel free to just do the old-fashioned way, shoot up your hand, and I can call on you, can ask your question that way as well. So let's get started. Model of execution. We finally want to start talking about the namesake of this lecture objective and start talking about exactly how programs execute when we hit the green play button. What actually happens in that thing? And specifically, we're going to focus on memory, what's happening in memory, and where our variables are going during the execution. To that end, today, the lecture task is more about testing and less about program execution. These program execution, the memory lectures, this one and Fridays, they really apply to everything. It's hard to write a lecture question very specific to these. Today's lecture question, more about testing and just getting more practice with Scala. So for this lecture task, like I said, objective, lecture task, write this greater circle distance method, which is going to calculate the distance between 2 points on the planet Earth, our lovely planet here. So given two locations by their latitude and longitude, calculate the distance between them as what we call greater circle distance, or as the crow flies. This is how long it would take to go from one point to another if you did the absolute shortest way to get between those 2 points on Earth. Taking into account that Earth is a sphere, this requires polar coordinates, it requires trigonometry, and a whole bunch of other math topics, mostly trigonometry, honestly, to calculate. It's not just the L2 distance or Euclidean distance where you would take the sum of the squares of each side and then the square root of that. It's not that simple. We have to do some extra math to be able to account for the Earth being a sphere. Earth's not exactly a sphere, but for this objective, we're going to assume it's a sphere with a radius of 6,371 kilometers, or 6,371 kilometers as the radius. So plug that into your equations when you do this. Now, this is not a math class, it's not a trig class, it's not a geometry class, so I don't expect you to really understand the math behind this of finding the length of a chord on a sphere, on the surface of a sphere. But I am providing you a link. It's in the homework description. It's on the slide right now as well. That link will give you a function that computes exactly this. It does exactly what you want it to do, but it's written in JavaScript. So this isn't a math or a trig task. This is a language conversion task. You have all this math in JavaScript. Your task is to convert that into Scala code, to get practice looking at code in one language and then converting it into another language. So I want to know that you can look at the JavaScript code, understand what it says, even if you haven't seen JavaScript, if you took 115, if you didn't take 115 here, that's fine. But looking at code in one language, no matter what that language is, you should be able to read the math dot, sign, things like that, and then convert it into Scala using Scala's math library to be able to get that same exact functionality in your Scala code. So that's what we want to do. This link also has a calculator where you can punch in 2 lat longs and hit go, and it'll give you the distance between those 2 lat longs. So generating your test cases, absolutely use that calculator. When you generate your test cases, you want to hard code the absolute truth of those test cases. So ideally, you want to compute your test cases outside of your Scala code, some way where you actually know the absolute truth of that. And for this objective, we'll use that calculator online, give it a good enough epsilon to account for any differences between that calculator and your code, and get your test cases going with that. This is true in general. I don't know if I mentioned this, so let me do it now. You should always be doing that. Always calculate your test cases offline, outside of your Scala code. This is one big trap that students tend to fall in. They'll write their code first and then use their code to generate their test cases and then they'll come to office hours saying, why doesn't Autolab like my code, or my test cases? Oh, it's because your test cases are wrong because you used your code, which was also wrong, to generate your test cases. Your test cases are supposed to verify that your code is correct, not be generated by your code. It's a silly thing to even do or even think of, but it's a surprising number of students will do that I assume, to try to do less work. It will cause you more work in the future because if your code's not right, your test cases are also not right, and then everything's just a waste of time after that. I personally, especially when it gets mathy like this one you have a calculator, so it's not too bad now. But when there's a lot of math going on, I'll usually open up Google Sheets and start a spreadsheet to generate a bunch of test cases. So however you can do it to get your test cases, but do hard code your test cases, compute them in some way that you know they're right, and then get them in your test cases, in your test suites. So that's your task today. Convert that JavaScript code into Scala code is effectively what it is, and use that website to generate your test cases. Unless you've already had lab, then you should have our test cases already. All right. Any questions before we get into it? What's up, Dragos? Let's do this. All right, let's quickly talk about interpretation versus compilation. And I want to just quickly talk about the differences between these two before we start talking about memory. So interpretation, this means that your code is read line by line, and each line is executed one at a time. Program starts at the first line, reads that line, executes that line, then moves on to the next line. In the debugger and in my slides, we're going to kind of pretend like our code is interpreted. But in Scala, our code actually doesn't run like this. It's actually ran by being compiled. It's a compiled language. So compilation is instead where your entire program, all of your code for your program, is looked over and then translated into another language, which that language may or may not be interpreted. For Scala's case, that language is interpreted, which we'll talk about in a second. But interpretation, your code is directly executed one line at a time. Compilation, your entire program is read, compiled into another language or translated into another language, and then that language might be ran and interpreted. So here's Python and JavaScript, so 115 if you took it here, both interpreted languages. One thing you'll notice, and Scala is a compiled language, which is the next slide, but one difference you're going to see between these, with your JavaScript and Python, you click go and it goes, like immediately, because the interpreter just jumps in, goes to your first line, and runs it. Scala, since it's compiled, your entire program is looked at and then translated to another language, and then that language is interpreted. So you notice when you hit go in Scala, there's a bit of a delay, there's a progress bar on the bottom of IntelliJ. It takes a little while. That's the compilation process happening. That's your code being compiled into another language, and then that language will be ran. So you can see this, you're already feeling the differences between compiled and interpreted. With an interpreted language, you're going to see a lot more runtime errors. In 115, you probably saw a lot of runtime errors, meaning your program runs, and then once it gets to a spot in your code where there's an error, it'll crash and everything breaks. So here's an example of a Python program. We haven't talked about classes yet. If that part doesn't make sense, that's fine. But here's a Python program starting with a main method where we're going to do just a little bit of math. We're trying to add 5 plus 10 is the ultimate effect that this program is going to have. We're going to create a new object where self.state equals 5. And then we're going to call this method add2state, which is going to add whatever we give this method to 5. So we gave this 10, so we're going to end up with 5 plus 10. Reassign that back to self.state, and then print out to the screen 15. No worries, no problems. Everything works great, and yay, we added 5 plus 10, not super interesting. But if we go over here, and instead of 10, we have the string ten, of course, not something that's going to work in this program. But what I want to emphasize is that when we run this program, since this is interpreted, this line is going to run, create an object where its state is 5, This line is going to run, which calls add to state, prints adding to state to the screen. Adding to state gets printed to the screen. And then once we get to this next line, we're trying to add the number, the int 5, to the string ten, and we're going to get a type error. Can't add ints and strings, program crashes, and everything dies. But adding to state did get printed to the screen. This program did run, and then we had what's called a runtime error. While the program was running, we came across an error. Didn't work. In Scala, that's going to be a little bit different. Here, again, without any errors, we're going to create an object with a variable named state equal to 5. We're going to call add to state with 10. And we're going to add 5 and 10 and print 15 to the screen. When we see this with an error, which is now going to be a compilation error, we have 10 here as a string being called on a method that takes an int. The compiler is going to see this. So while the compiler is attempting to translate your Scala code into another language, it finds this error and says, whoa, what's going on here? You can't do that. And it's going to stop the compilation process and yell at you with an error message. Or in IntelliJ, it's going to underline this with a red line. But in either case, you cannot run this program. You can't run it at all. You can't get to the point where adding to state is printed to the screen, because you can't run a single line of this code because the compilation process failed. So if you ever have a compiler error, you can't run anything. Now this might sound like a pain, but this is actually extremely helpful in programming. With a compiled language like Scala, also Java, C, C++, all compiled languages, you're going to get more compiler errors, which might seem frustrating sometimes. I've learned to love them, so I love seeing compiler errors, or no errors, obviously. But the compiler is doing a lot of work for you, checking your code and telling you that, hey, you have a mistake here. You don't have to run this. Like this code, you'd have to run and do some debugging process. You have to enter your debugging process to figure out what's going wrong here. But with Scala, it's just going to yell at you right away and say, hey, fix this. The error's right here. Fix this before I run your code. So it actually helps you find and fix a lot of your bugs before you get too deep into the development process, before you write too much code. It's just going to say, hey, that's a string. You're trying to add it to an int. Fix this before we move on. So the compiler does really help us in that way. And especially, you can get into some really big issues where if this line is in a conditional and you haven't written a test, you haven't tested where that conditional is true, this whole program could run and act like it's fine until you run it with a case where that conditional is true and that line is executed and then your program crashes. Those bugs can be a little harder to find. Scala is going to look out for us and the compiler is going to look out for us and find those bugs without us having to search very far. So Scala is compiled into a language called Java bytecode. This is the same language that Java code is compiled to, and also several other languages. There are several languages that will compile down to Java bytecode, which is ran on the Java virtual machine, the JVM, which if you've ever had your computer yell at you to update your Java, they're talking about the JVM. Whenever you update that, you're updating the JVM, which is installed on like every device on the planet. I don't know, not quite, but fairly close. Java runs everywhere. Java bytecode runs everywhere, so your Scala code is running everywhere. And in addition to that, you can, since Java and Scala both compile to Java bytecode, you can mix these languages in your code. You can have some Java code and some Scala code, compile them both down to Java bytecode, and the Java bytecode runs just like it was one language. The Java bytecode, the interpreter, the Java virtual machine will interpret the Java bytecode and run that as an interpreted language. And the JVM doesn't care or even know that that code came from Scala or it came from Java or it came from Kotlin. It doesn't know or care. It's just all the same. So the benefit of this, one of the benefits, is we can use Java classes in Scala. In fact, if you do math dot in Scala, you're using Java's code. That's some Java code. A lot of the built-in functionality in Scala is just using the Java standard library. This is also why we had to install the JDK, the Java Development Kit, to be able to get the Java compiler and all the Java classes, all the Java standard library. That's why we did that, to get all of that in our code, because can't use Scala without Java. It's built on top of, effectively built on top of Java, at least on top of the infrastructure. And we will actually use other Java libraries in this course. For writing GUIs in the next learning objective, we'll actually use a Java library for that, JavaFX, plus ScalaFX, which is a layer on top of it to make it Scala friendly. Ooh, that's a good question. Yeah, no, you can't. So the question is, if you have experience in Java, can you use Java for parts of the lecture test? I don't know, kind of. I think Lana's got a good answer on this. I didn't read it yet, but anything that's specified in the homework doc, write a method, name this, that takes these inputs, these outputs, that has to be Scala, because I'm compiling your Scala code. Actually, no, I don't think you can use any Java, right? Because in Autolab, I'm compiling your Scala code, so it wouldn't really work using any Java. Yeah, that wouldn't work. Just the way I have the grader. All right. Any questions on interpretation versus compilation before we get going? Let's talk about memory, baby. All right, so RAM, random access memory, or just memory these days. The RAM sticks that you have in your machine, where if you don't have enough of it, your machine goes crazy slow. Let's talk about this stuff. This is where everything in your program lives. Until you're doing file I/O and talking to the disk, which we do, sometimes we did a little in 115. Besides that, everything lives in RAM. Every time you put val or var, that's going in RAM. That's saying store this in RAM. So everything's being stored in memory in this thing. These sticks are effectively giant arrays, and then you have multiple sticks. Your OS is going to treat them as one large array of memory. That's why it's called random access. Random access, like an array in our programming languages, where you can access a value by index. That's exactly what's going on here. Random access memory means I can get any value out of this array if I know its index. I can go grab the value at that index. That's what your RAM is. That's what your RAM's doing. RAM is extremely fast, much, much faster than hard disk. Even if you have an SSD, reading from RAM is significantly faster. The disk is very slow. Even SSDs are very, very slow. SSDs are better, but still ridiculously slow. The trade-off there is RAM is way more expensive. If you price it out, within like a terabyte SSD is about on the same order of magnitude as 16 gigs of RAM for significantly less memory. It's if you think about trying to get a gig of RAM, if you ever price this, if you ever built your own machines, if you just get pre-built machines, you might not have thought about this before. But go on Amazon and price out RAM versus hard drive. The price is astronomically different. They have two completely different functions. Memory is meant to be very fast but limited, and hard drive is meant to be more long-term storage, where we're just storing large amounts of data, and it can sit there and be slow to read and load up. So when we run our program, what our program is going to do, or what the JVM is going to do, is talk to the OS and say, hey, I got this program that needs to be ran. Could you give me a slice of that memory, please? And the OS, as long as it's in a good mood, is going to say, as long as things aren't breaking, and is going to say, okay, here's a slice of RAM. You can have this section of the RAM and use that for your program. And this will be just like an array. We're going to have these values. In reality, I did this to fit on the slide. In reality, you're going to have a lot of indices, a lot of bytes of storage for your slice of RAM. But you're going to have some slice of RAM that you can use for your program. You're going to have, if you read that article that I linked for today, the one about the stack, you're going to see some program data, some extra information on the bottom of the stack. For 116, we're going to ignore that. That's just not important for our purposes here. In later courses, they might talk about more of this. I believe they do in 220. But for our purposes, we're not going to worry about that so much. We're not actually going to worry about command line arguments either. We don't do any command line arguments in 116. But the program memory, the rest of it, that's where we want to look at. That's the working memory. That's kind of like the scratch paper for our program to run. And that's the one we really want to talk about. Yeah, you can try to download more RAM. Swap memory works. I don't want to go too far down that rabbit hole. But if you run out of RAM, if you ever notice your computer just really suddenly slowing way down, if you use all of your RAM, your OS is going to start using hard drive as memory, as extra memory, and you're really going to feel how slow disk is compared to RAM, because your computer will just almost completely shut down. It'll be almost unusable once you start using swap space. Once you start using hard drive as RAM, it's extremely slow, extremely, extremely slow. If I've ever had that happen, that's the difference between RAM and hard drive speed. Even with an SSD, once you start using swap space, it's all but over. So a stack is a last in, first out data structure, meaning that we can only add and remove values from the end of the stack. Whatever the next available memory is that we haven't used, that's where the next variable we declare is going to go. And we can only remove variables from the end of that stack. So we're never going to have gaps in the stack where we have empty values. Whenever we call a method, and there's a bit of text on these slides, by the way. I do have an example following this stuff, but I just want to get all the information out there and then reinforce it with the examples. So we have a stack frame. Whenever a method is called, it's going to create what's called a stack frame. A stack frame is effectively an isolated environment for variables to be stored. And when you're inside a stack frame, you can only access the variables declared inside that stack frame. So whenever you're inside a method call or a function call, you can't access the variables that were declared outside of that function. You may have kind of intuitively known this, but we're going to make this more explicit now. When you have a function call, you can't access the variables outside of that function call because it's executing inside its own stack frame. Every method call gets its own stack frame, and the program starts in the stack frame for the main method. So once your program starts, a stack frame is created for the main method, and then each method call or function call after that is going to have a new stack frame created, which is like its own little isolated environment, its own little isolated portion of the stack to be able to do its computation. And variable scoping. So the two big things we want to talk about are stack frame, well, I guess three. The stack is the overarching topic we're talking about. Stack frame created when a method is called, and then variable scoping. When do I have access to which variables that have been declared? Variable scoping, every time you hit a new code block. So this could be a conditional, an if, an else if, an else. It could be a loop. Or just nothing, I guess. I want a third thing to complete my list. Or nothing. If you just put braces with no if, no well, no for, if you just put braces, you can create a new code block that has no control flow attached to it. You can just create a new code block for no reason. There's almost never a good case for that, but if you want to do it, you have that option. So every time we hit a code block, it's going to be treated differently. The variables that are declared inside that code block are going to be treated differently on the stack. They're going to get their own portion of the stack, which is not quite as isolated as a stack frame, but it will be a little bit isolated. So specifically, if I create a variable inside a stack, or if I'm working inside a stack frame, inside a code block, I can access the variables that were declared outside of that block as long as they were declared in the same frame. And I can actually have well, I don't want to get into that yet. We'll talk about that probably Friday. And every time we hit the end of a code block, any variables that were declared inside of that block are destroyed. They're removed from the stack. They're going to be the last variables on the stack, so we can delete them, and we're just going to get rid of them. We're going to blow them up as soon as we hit that closing brace. Anything that was declared after that open brace, gone. It's all destroyed. Okay, so that's all the information I need you to know. Technically, that's all the information I need you to know for today and Friday for the rest of Learning Objective 1. But we need a lot of examples because that was a lot of text, that was a lot of information. So let's hammer this down with some examples. We're going to have a lecture and a half of examples to really show you what's going on, what I mean by all this stuff. So let's start with this one. Compute factorial, this is the only example for today. This will run us the rest of the lecture. All right, when did we start this? Oh yeah, this will definitely run us to the end of lecture. I probably won't be able to go to IntelliJ today. If I go to IntelliJ, I'll just run this thing. So this compute factorial, we should all agree that this works, I hope, as long as I didn't make any silly error that I haven't caught. Compute factorial, given a number, return that number factorial. So if the input is 3, return 2 times 3 is 6. If here, like the input is 5, should return, why do I back myself into corners like this? 120, I think it is. It should return 5 times 4 times 3 times 2. Technically times 1 as well, but it's just multiplicative identity, so who cares? You'll notice that this is not Scala code. I'm trying to keep this example language independent. I want to focus on the concept of the stack, of the memory stack. This concept is going to apply across languages. The things we learn about stack and eventually heap in Learning Objective 2. Heap memory is different than stack memory. We'll talk all about it. You need to know those concepts. And hopefully this is sounding familiar to you. In 115, it's all about the concepts. I don't care if you can write a conditional in Python. I care that you understand what a conditional is doing and how that's affecting the control flow of your program. Same thing here. I want to make sure you understand how RAM works. I don't care that you know how RAM works in Scala. So this is intentionally language independent. Just by accident, it does compile as JavaScript code, but that's strictly by accident, just by the keywords that I used. So let's step through this program. We're going to pretend it's interpreted or that we're running Scala in the debugger and look at everything that's going on as this program executes with a strong focus on the stack. By the way, a heads up for your quiz next week in lab, this is what your quiz is going to look like. I'm going to give you code like this, and I'm going to ask you to walk through the program while explaining what's going on in the stack. So these examples today and Friday, it's exactly what I'm going to ask you to do on the quiz. Here's some code. Talk to me about the stack. What's the stack doing? And I'm going to have some variables with the same name. Like I have 2 i's, I have 2 n's in this program. I'm going to have duplicate variables like that. And might get trickier than this. It'll get like the Friday examples. And I'm just going to, talk to me about the stack. So that's a heads up of what that quiz is going to look like. So I'm going to start with the first line, which is going to take the command line arguments. Again, not something we're worried about in this class. For your own projects, you might want to use command line arguments, just not something that we're going to mess around with in 116. Honestly, we got enough stuff to learn. I got enough stuff to teach you. Anything I can cut like that and not talk about. If you're interested, just Google it. It's not that hard. It's just one extra thing we'd have to think about. But the command line arguments are the very first thing that go on the stack when the program's called. If you're curious, I'll give it very brief. This is if you want to give extra parameters to your function or to your program when it's called. Like if you're calling it from the command line, the reason they're called command line arguments, if you run your program and then a space and then more arguments after that, those arguments go right in this variable. It's an array, and that's where you have all your command line arguments. Just something we're not going to mess with, though, in 116. So those are going to be the first thing on the stack in our program. And as we go through, we're going to add variables to the stack every time one is declared. So whenever we have a variable being declared, it gets the next spot on the stack. And that's where that variable is going to be stored. So here I'm declaring a variable I, assigning it the value 5. That's going to get the next spot on the stack. The next spot on the stack gets a variable named I and a value of 5. And any other variables that are declared just get that next spot in the stack. Next, we hit our first function call. This is where we want to talk about stack frames. So I have a call to compute factorial. So a new frame is going on the stack, which starts a completely isolated execution environment effectively. So once I call this method, we go into like a whole different world. It's still on the stack, it just gets the next spot on the stack, but there's a line. Like these beginnings of a stack frame, you can't cross that. That's a barrier, you cannot cross that and read those other values. So we're in a completely new environment. The first thing that goes in that stack frame are the parameters. We have one parameter here named n, and we're going to assign it the value 5. We definitely want to use that inside this stack frame for the method. We want to be able to access, we need that to be able to access that to run this method. So that's going inside this new stack frame. We're going to declare another variable, result, assign it the value 1 to initialize our multiplication for our factorial, and put that in the next spot on the stack. So we have two variables inside the stack frame, n and result, with values 5 and I. Now, no matter what we do inside here, and we're going to see this with I, actually, I'll just advance to the I. Now, for the for loop, we're going to run this initialization statement. I declare a variable named I with the value of 1. This goes inside the loop block, so we have another barrier. This one's more of a soft barrier than the stack frame. First, I want to talk about this I. So this I, no matter what we do, this I is going to be different than this I. No matter what we do, this I inside the main stack frame, we have no access to that. We have no knowledge of it. We can't see it. We can't do anything with that value. We can't read it. We certainly can't change it. If we have like print I to the screen right here, we're going to get a compilation error because I does not exist. We cannot escape the stack frame that we're currently in. I does not exist there, which means since it doesn't exist, we're free to reuse that variable name. Inside our function, we can create a variable named I without worrying about any other method that's calling this method or function. I'm mixing method and function here because I put function in the example. We can reuse that without worrying about, because whoever called this method, we have no idea what they declared, what variables they declared, what they're using, what they're doing. It'd be a real pain if we didn't have stack frames, because we'd have to be like, okay, any variable that anybody who ever calls this function ever, we can't use any of those names. Well, that's just not feasible. It's not going to work. There would be naming conflicts all over the place. Things would break so easy. Wouldn't work. So we have no access to anything outside of the stack frame, and we like it that way. So we can use whatever variable names we want. I equals 1. I hasn't been used inside the stack frame, so we can use it. We also started the beginning of a loop block, and the initialization of a for loop, including the name of your elements that you're iterating over in Scala, whatever variable you're using as the iteration variable in a loop, is inside of that block for that loop. It's declared inside of that block. So now we're going to check our conditional. I won't belabor the loop stuff. Hopefully you all understand well in depth how loops work. But we're going to check I less than equal to n. What I do want to focus on, when we do this check, we have to look up I and n on the stack. When we look for each one of these variables, we're going to start looking inside the block that we're currently in. So we're going to look for a variable named I inside the loop block. That's where we're currently executing. That's the current block that we're executing in. And lucky us, we found an I there. So I is going to be 1 in this case. Now for for n, we're going to do the same thing, and result in a second. We're going to do the same thing. We start looking inside this block, and we're looking for a variable named n, and we don't find one this time. We don't find a variable named n. So then we're going to expand our search to the next block, which happens to be the stack frame, and we're going to look in this stack frame. Hey, stack frame, do you have a variable named n? Yes. Perfect. That's the n that we're going to use. So now we're going to take n, the value 5, I, the value 1, and then execute our conditional here. Same thing with the result. In I again, we find I inside the block. We find n inside the stack frame. That search will continue to outer and outer blocks until you hit the stack frame. That search will not extend past the stack frame. This is a very hard barrier. You cannot cross this. But each block, you're going to search independently. So if we had nested conditionals and loops and had all kinds of blocks inside blocks inside blocks, we're going to keep expanding our search until we find the variable that we're looking for. If we get to the stack frame and haven't found it, then we got a compiler error or a runtime error, depending on the language. We got some kind of error, variable can't be found. Then we're going to run through the loop. I already said the important stack stuff that I want to say. I'm not going to go through the whole loop, but by the time we get to the end of it, result is going to be 120. Hey, I was right earlier. 120. I is going to be 5. And we've reached the end of the loop block. So we hit a closing brace. Now we want to look for anything that was created inside this block and blow it up. So once we hit this closing brace, this variable I no longer exists. It's completely gone. It's removed from the stack. It does not exist. It's like it was never there. No memory of it exists. It's gone. We can't access it again. Can't access it outside the loop. This is a common 115 error when you're first learning how to program, is you'll create a variable inside a block, and then after that block is over, you'll try to return that variable. Well, that variable doesn't exist anymore. You'll be screaming at your laptop, it's right there. It's right there, just return it. But after you hit the end of the block, it's gone. It's destroyed. It's not on the stack anymore. You can't access it anymore because it does not exist anymore. So that's why you have to declare your variables outside of that block. I declared result before my loop because I know I need to return that after the loop. So if I declare inside the loop, I'm going to have all kinds of trouble. Declare it outside the loop, now it exists after that block is destroyed. This is also why if you have like two loops, if you have one loop, that loop ends, and then another loop in your program, and you use the variable I for both those loops, it's perfectly acceptable because after the first loop, I is destroyed, then another I is created inside the next block, and then you can use I again. You can reuse variables like that if they're in different blocks. And then when we return, we hit the return value. We're hitting the end of a block again. This block happens to be the function block. So now we're destroying the entire stack frame. We get to the end of a method call or a function call. The entire frame is destroyed along with any variables that were declared inside that frame. They're all gone, they're all destroyed, and in this case, our function is going to return the value 120. So all of that, creating the stack frame, creating the loop block, all this stuff that's going on the stack, all of that was to get to this return value of 120. The entire stack frame resolved to the value 120, and that's what we're giving back to the main stack frame, which is sitting here waiting for that return value. So everything that had to do with that method call is over. It's not in memory anymore. It's not on the stack anymore. And we get this value 120. Here we can declare variable n and store that 120 inside that variable. And again, I'm reusing n. It doesn't interfere with this n because that n was inside that stack frame, which was destroyed. That n's gone. I can reuse that variable name, no problem. I'll just print n to the screen. At this point, no memory of that function call. It's as if it never even happened. That function call just resolved to 120, and we don't know how at this point. We can't look back and figure out how that happened. And then we reach the closing brace of our main method. That's our top level stack frame. That means everything to do with our program is destroyed. Any variables that were declared, gone. Blow it all up. Free up that RAM. And give that RAM back to the operating system and say, thanks for letting us use this. And there's no memory of our program. It's all gone. Completely gone after the program ends. All that RAM is freed up and given back to the OS. Yeah, well, you have to walk through each. So the question in chat, actually Lana's got this. Yeah, the questions won't be tedious. Like I won't ask you to write out every step of a loop or something, but you might have to trace through each step of the loop just so you get the right answers in the end. But I won't ask you to be like, okay, now I increments, now it checks the conditional again. That's 115 stuff, we're done with that. I won't ask you to report all that on the form. Because there's specific things. I want to make sure you understand how the stack works and how variables are stored in a program. I know you can trace through a loop. It's just something we don't have to test in 116. If you can't trace through a loop, you're going to fail anyway. We don't have to ask you to do that. Anyway, this might have sounded a little harsh, but so on the stack, the only variables that are stored directly on the stack are these ones, what I'll call primitive values: doubles, floats, ints, long, short, char, byte, boolean. That's a comprehensive list. Those will go on the stack. Everything else is going to go on what's called the heap, which is something that we're not going to worry about till next week. It's not going to be on your LO1 quiz. It's an LO2 topic. But any of these are going to go on the stack. I put primitive in quotes. If you've had Java experience, you'll be like, but those are just primitives. Like, you don't have to put that in quotes. Everything in Scala is an object. So there's no concept of primitives in Scala. But when your Scala code is compiled down to Java bytecode, these objects do correspond with the Java primitives, and they do go on the stack as their actual values. I can't go too far into it than that, but until we talk about the heap. When we talk about the heap, I'll bring this up and talk about it some more. But these values will go directly on the stack. Anything else is going to go what's on the heap. So for quiz next week, you're going to see these types, and only these types, nothing outside of those. Which the notable thing that's missing here is string. You won't see strings. They don't go on the stack. And my little caveat, I got to mention this. Compilers are sophisticated, very sophisticated programs. What's actually going to end up on the stack and heap and how memory is actually managed might be different than the model that we're seeing here. But what's important is that you understand the concept. This is effectively how things are going to work. When you're writing your code, that's how things are going to behave in your code. So that's how we're going to draw it up visually. What the compiler does might be 100% accurate, probably at least completely close, maybe 99% true to this. But there are some really crazy compiler optimizations that might put things that are supposed to go on the heap in the stack and et cetera. We're going to ignore that, but if you want to learn about compilers, we have a whole course about compilers taught by Dr. Alphonse. You can take that and learn all kinds of cool stuff about compilers. We're going to try to keep things simplified in this semester. So these go on the stack and everything else goes on the heap. That's where we're going to draw the line of this model. Which brings us back to our lecture test. I do have time to hop to IntelliJ real quick. I want to do one thing over in IntelliJ. Memory. So let me do it like this. And IntelliJ is going to kind of give away the answer. Oh, right, I can't do that exactly. I can do this. IntelliJ is going to kind of give away the answer here, but is this valid? This one's a little too tricky, actually. I wouldn't like this one, but let's run this. We might actually, to be honest, I don't know 100% know. Yeah, it does. Okay. I thought I might have gotten a circular reference there. But this actually runs. This works. This is fine. Everything's perfectly fine with this. I'll have more examples like this on Friday. But since this n is declared as part of this for loop block, it doesn't interfere with this n, which is declared inside this stack frame or this function block. So I can have duplicate variables, variable names in the same block, and then whenever we're looking for a variable, like this n here, we're going to look, okay, we didn't find an n yet because this n hasn't been declared yet. So we're going to look for an n, we find it outside the block in the stack frame, and this n is going to relate to the parameter. And then inside the loop, when we have this n, it's going to, and you can see IntelliJ pointing to where the variable is declared. This n, when we look for this n, now this n has been declared. We're going to look inside this block, find this n, and stop our search. Even though another n exists outside of that block, we're not going to find it because we already found an n and stopped our search. This one's a little too tricky for the quiz, but I will have instances on the quiz like this where you're going to have multiple variables with the same name in the same stack frame, and you have to be able to see which one is going to be used based on which block it was declared in. So things can get tricky when you understand how the stack works. Like something like this, if we show you this in 115, you'd probably just say syntax errors that you can't do that. This is absolutely something you can do. We just saw it run. Sometimes when you do this, like if I called this n, I get issues there because I have a circular, I think it's just assignment to val, actually. Yeah, reassignment to val. So certain things you won't get away with, but a lot of things you can do, things you might not think you can do. With that, I'm out of stuff to talk about, so see you everyone Friday. Take care.